Hi everyone, I'm not feeling well today, so I've made a video. We are going to go through the inquiry questions. So what I'd like you to do today is once I'm done what I'm doing, you're gonna complete questions 12 and 15 on page 94, and you're gonna catch up on any work that you didn't do up until now. To get to this lesson, let's scroll down, and we're actually going to scroll past lesson 2.3, okay, and we're going to get to page 10, I believe, and we're going to do these questions. So you guys actually did this pizza question for homework, okay, but I'm going to take it up. Okay, it is a little different than anything we've done in class. Okay, so here I have a pizza of radius x. And part A is asking me for an expression for the area of the pizza, and because it's a circle, it's pi r squared. In part B, it says, okay, we're gonna make the radius a little bit bigger, and we need an expression for the new pizza's area. So what I have to do is remember that I need brackets around the x plus 5 because it's the entire radius squared. And now in part C, it says, how much greater is the second area? So what I'm gonna do is say D for difference. And now I'm gonna call the large pizza AL and the smaller pizza AS. And I know the difference is AL subtract AS. And now I'm just going to sub in the expressions I got from A and C, A and B, and just put it in here as a difference. Now what I need to do is expand my brackets. And if you recall, a power of 2 on a binomial means I have to repeat the binomial. And then I am going to expand it. Okay, and I will simplify. So I get pi x squared plus 10 pi x plus 25 pi minus pi x squared. What you'll notice is that these guys cancel, and my final answer is 10 pi x plus 25x. So hopefully you got that, and hopefully that is the question in the back, answer in the back. Okay, for the next one, on here I initially wanted you to do page 94, question 12, but this one's actually for homework. Number 12 is, so I'm going to do 13 instead. And I know this seems like a complicated question, but if you break it down, it's really not that bad. Okay, it seems that the sum means add, okay? The sum of the squares are powers of 2, sum of the squares of 2 consecutive even or odd integers, 2 consecutive even integers. So consecutive even integers would be 2, 4, 6, 8, and so on. So 4 and 6 are 2 consecutive even integers. 4 and 8 would not be. 1, 3, 5, 7, 9, etc. The consecutive integers would be ones beside each other in that order. Okay, so I'm just describing, or the words are just describing these two examples. But what's interesting is whether the numbers are consecutive and even or consecutive and odd, the answer seems to always be even. So this question is asking me to go through A, B, and C to show why. Okay, so it's saying, let n represent the first integer. So then what represents the second integer? Well, if n represents the first integer, for example, 4, okay, then n plus 2 has to represent the second integer because it's 2 away. So 7 plus 2 is 9, 4 plus 2 is 6. Okay, and then the question asks, what expression represents the sum of the two squares? Essentially what is above there. So the sum of the two squares, which I'm going to call S, will be the first integer squared plus the second integer squared. And now part C asks, Use algebra to show that the result is always even. Okay, so what I'm going to do is basically all I can do in this question, which is to expand the second part of the equation. Okay, so I'm just going to use distribution, and I end up getting 2n squared plus 4n plus 4. Now, I have 3 terms here, and it must be true that each of these is even, and when I add them together, I'm going to get an even answer. Or a better way to think about it is, no matter what n is, as long as it's an integer, whatever this is, it's being multiplied by 2, so the result will always be even. Okay, so therefore the sum of 2 consecutive even or odd integers is always even. Okay, thank you guys. Oh, I forget what our guy looks like. I got a thumbs up here. All right, guys, I will see you next week. Enjoy Thanksgiving.